Hi gentlemen, welcome back. The purpose of this video is to continue talking about rational zeros, finding zeros, and linear factorization. So it's a continuation really of the last video. We're just going to do some examples, and I want to highlight a few different things in the following one. So let's get started here. Let's look at our first example. It says find all the zeros of this function right here, given that 3i is a 0. So now all of a sudden we have an imaginary 0. Okay, so that's not going to cause us too much problem because we're going to basically go about it the same way. If 3i is a 0, I can still do synthetic division with that. Okay, and what we should see is, again, I should get a remainder of 0. Just because this is imaginary doesn't mean that I shouldn't still get a 0 remainder. Alright, so let's go through this. Bring the 1 down. Now I get 3i when I multiply. I get 1 plus 3i. Now again, it's a little more work, but it's not something that shouldn't be too much difficulty. When I multiply here, I get negative 9 plus 3i. And let me just highlight this for you guys how I did that. I have 3i, and I want to multiply by 1 plus 3i, like that. Okay. I distribute through, so I get 3i plus 9i squared. Remember that I squared is negative 1. So this is going to be 3i minus 9, because I squared is negative 1. And that's where that term right there came from. And again, now when I bring this down, the 9 and the negative 9 cancel out. I get 3i. I get 3i squared when I multiply up. I get 9i squared when I go 3i times 3i. And so, let me just write that for you. 3i times 3i, like this, here, is equal to 9i squared. Again, this is negative 1, so that's where the negative 9 comes in. And again, my remainder is 0. Okay? So what does that all mean? Well, that means that I can factor all that. Let me get all this out of your way. To this. Okay? And again, don't get intimidated because we have complex numbers in here. All right, so here's my first root because I know this is a root. Then I have x squared plus 1 plus 3i. That's this term. Remember, synthetic division, I start with one less degree here. So that's going to be x squared, 1 plus 3i times x plus 3i. So this is what I have here. And don't let this term get you all confused. All right, just coming from my synthetic division. Now, if I continue, I got to make use of this fact right here. This is going to save us some time, so make sure you know it. Complex zeros occur in conjugate pairs. So if 3i is a 0, that this right here tells me that negative 3i is also a 0. And so let's make use of that fact. So what I want to do is now I want to factor this part, making use of the fact that negative 3i is a 0. And so again, I'm going to use some synthetic division. Here are my coefficients, 1, 1 plus 3i, and 3i. Use my other 0, negative 3i, and let's see what happens. Bring the 1 down, negative 3i, 1, negative 3i, and 0 remainder. So it works. Okay? So that tells me now that this term can be factored down to x minus 3i, x plus 3i, x plus 1. I have one rational 0 right here, and I have two complex zeros or imaginary zeros. Okay? And there are my zeros. And this is my linear factorization. Everything is a linear term here. Okay? If I wanted to graph this, again, we could look at the degree. The degree here is 3. We know the leading coefficient is 1, positive, which tells me, again, you guys should know, just from what we've talked about so far, that because odd degree and its leading coefficient is positive, I'm going to go off to infinity there, and I'm going to go down to infinity on this side. Okay, and we got to fill in the pieces in between, and we can use our zeros to do that. And again, at most we're going to have 3 rational zeros. Here we have 1. And the other thing that we're going to have is at most 2 turning points. Okay. The end behavior, it's going to rise to the right, fall to the left, and we have one rational 0. Okay, and there's the graph of that. Let me get this out of your way here. Okay, and hopefully that makes sense. Here's my 1, 0 right there. Okay, doesn't look like I have any turning points. This function's always increasing, right? It's never decreasing, and so we don't have any turning points in this particular problem. Okay, let's do another one. Now we have x to the 4th. On the right is a product of linear factorizations. Okay, so I want to find all the zeros here of this function. Okay, we know our possible zeros. We use our rational zero test. Remember, it's p over q. P are the factors of the constant term right there, which is going to be plus or minus 1, plus or minus 3, and plus or minus 9. Okay, q is easy here. Q is just plus or minus 1 because the coefficient of the leading term here is 1. Okay, so that's pretty straightforward. Again, what would I like to do? Well, I'd like to find out one of them. I just want to test the negative values here. Why do I just want to worry about negatives? Because every sign here is positive. And if I just plug in positives, all these positive terms will never get a 0. So I would test the negative ones, and I find that negative 3 is a 0. So it gives me a starting point. Once I have my starting point, I can do my synthetic division. Bring the 1 down. 3, negative 9, 1, negative 3, 3, negative 9, 0. So now I can factor this, and I get this term. Now I have, here's my first 0, x plus 3, x cubed plus 3x squared plus x plus 3. Try to find another one, possible rational roots here. Again, doing p over q, plus or minus 1 and plus or minus 3. Here we go, next slide. Again, we just want to test the negative numbers again because they're all positive signs. We find out that negative 3 is a 0 again. So let's do synthetic division. 0, 0, 1, negative 3, and 0. So again, it's a root. Tells me that I got 2 roots now. I got a double root. We should know what that means. We'll talk about that when we do the graph here. But I got x plus 3, and then this is, again, synthetic division. We go 1 less than the degree here. So I get x squared, no x term, plus 1 right there. The zeros of this, if I solve that, if I set x squared equal to negative 1, that's the solution to making that 0. I get x is equal to plus or minus I, or the square root of negative 1. Now I can write this as my linear factors, x plus 3 squared, x plus I, x minus I. Okay, I could actually write this x plus 3, x plus 3, x plus I, x minus I. Here are my zeros. Again, this is a double root. So if I want to look at graphing this, again, we should look at degree is 4. Leading coefficient is positive. So right off the bat, we know that I'm going to finish up here, and I'm going to finish off going to infinity, something like that. We got to fill in the pieces in there. Okay, end behavior, we're going to go off to infinity on both sides. I have one rational 0. It's a double root. What does the double root mean? It means that we're just going to touch at negative 3, but we're not going to cross the axis. Okay, let me get this out of the way. Remember, if it was an odd, if it was a triple root or something like that, it would go through it. But we only have a double root, so we're only going to touch the curve at that point. Okay, so we're going to touch the point right there. It looks like we have, again, at most I can have is 3 turning points because I have degree 4. I can have 4 rational roots or real roots. Right now I only have 1. It's a double root, just touching the curve. Looks like I'm going to have a max, a min, and then I'm going to go off to infinity on both sides. Okay? Here's some practice. You already read the section, but I want you to look at these examples and do these problems. All right? So the only new thing that we learned in this particular video is that complex zeros come in conjugate pairs. So if 1 plus I is a 0, then 1 minus I is also a 0. Okay, so make note of that. So if I'm giving you 1 and it's a complex 0, its conjugate pair is also a 0. All right? Any questions, make sure you guys are emailing me. We've got a couple more sections to cover, and then we'll be good to go and get ready for that week 2 problem set. Okay, fellas? Have a good day.